second task. In the second task, what we're just going to do is to have, just going to review the design problems of every drainage system. And you've got like 20 minutes to just go through with that example. So for this task, we're just going to learn how we're just going to use the SWMM software to design every drainage system. And the purpose of that is to minimize the peak flow by finding the best size of the culverts and other like the elements of the sewer system. And in order to just make sure that we can pass safely the specific like the floods in the system by using some specific like the design storm. That in this case, we're just going to look at a flood with a 100-year return period and 2-hour duration without any flooding at any node in the system. So let's just very quickly in a few minutes review what do we mean by 100-year return period. I believe that you are all familiar with this kind of like a curve. This curve is called like the IDF, intensity, duration, frequency. If you're not familiar, please make sure to have a look at the relevant hydrology references to understand what is all defined and how we're just going to define this kind of like the curves. Normally, it is available to civil engineering. Hydrologists normally develop these curves for any specific area. In some like the area, for example, US, there are some specific websites that you can just easily find this kind of like the IDF curves. But for example, if you look at this curve, the horizontal axis shows the storm duration. For example, any duration of the storm from like a 15 minutes up to like the 250 minutes. The vertical axis is the intensity. It's like the expressed in millimeters per hour or inch per hour in English units. And each curve represents a specific return period. For example, we're just going to work on a like from 1-year return period up to a 100-year return period at the top. So for each curve, you need to just first of all specify the duration. For example, in our case, like it's 2 hours. 2 hours is like 120 minutes. And for example, for that specific structure or the sewer system, we're just purposing 100 return period. For example, 100 return period is here is like an orange curve, 100 return period. For example, if I'm just going to try to just find this one, I'm just going to go here, and then you can just see the vertical axis. So this is something around like, let's say like, for example, average like a 25 millimeters per hour. So 25 millimeters per hour means that for 2 hours means that 50 millimeters. Okay, for 50 millimeters, we can have like a rainfall, and then is like a total depth. We need to just convert the total depth to the height graph. Height graph is the variation of the intensity over the, for example, specific period that we have a rainfall. In this case, we said like the 2 hours. So 2 hours, for example, we're just going to have something like this. And in hydrology references, there are some specific and popular methods that you can convert the total depth to like this kind of like a stepwise like the variations of the intensity. For example, you can just normally just have like a bell shape or like a triangle shape. So you can refer to those relevant references and you can derive your height graph variations of your own rainfall or for a specific rainfall or return period. And just bear in mind for a specific structures or like the hydraulic structures, you can look up for relevant references what is the required return period based on the standards and the codes that is required. For example, here you can see for the different types of the highway, we can have like the return period requirements from 5 to 10 years. And if it's like a high traffic, for example, you need to just take into account or analyze with the 50 years to 100 years. So depending on the local or national standards that you're working with, you need to pick up a proper return period and use and analyze with a different return period. So that is the situations that we have. So, and there's a one reference here that you can just use this reference as well to just use the this kind of like a stepwise duration. So that's like a one reference for you if you want to just see more information about that. So if you want to just pass this one, just before to go and show you examples in the SWMM, I'm just going to show you some of the like the key elements in the SWMM. First of all, in the hydraulic elements that we have in SWMM, there are some like the key components. First one is like nodes. Nodes is the connecting the pipe. All the pipes are connected through the nodes. And you can see here, this is like a real swing system, for example, is connecting the pipe, and all pipes are joined in a like nodes. This is like the nodes. But in the modeling perspective, you can see the node is like a dots, and the pipe is shown by using a link. But the nodes in the SWM is shown in different like purposes. One, the common one is like a junction. It can use for manholes, point of change in conductor slope or cross section. If you want to just have that one, you need to define a new node. Or there are some like the other like the points like the divider, storage unit, and outflow as well. Outflow is like the most downstream point. That's the flow is discharged. For example, to another like a system could be, for example, a river or stream or like any other receiving water bodies. The other main elements is link. So the link is also very popular in the SWM. Different types of the links is shown here. For example, the most popular one is a conduit. Conduit could be like the open channel or like the open or natural conduit or closed conduit. So all types can be defined in the SWM. And you can see here the way that we connect the SWM, the link to the nodes, you can define some specific parameters called offsets. Okay, so offset is like the difference between the invert level of the node and the invert level of the conduit. So just bear in mind. So you have like the invert of the inlet and outlet. Inlet means the upstream point, and outlet is the downstream point of your link. Why upstream and downstream? Because as you know, the link or the sewer system works based on the gravity. So once they work on the gravity, you have to define which point is the upstream and which point is the downstream or inlet or outlet. So the same. So the different types of the links can be defined in the SWM. The most popular one, as I said, is like the conduit, but you can just define links as like the pump, orifice, weir, and outlet. That we can see in other examples here. Okay, so let's see what we're just gonna do in here. So all explanations that we're just gonna have. So this is like our sewer system that the example you're just gonna go through in example 2 that we're just going to practice. Please just have a look at this example. This is like the catchment area that we have, and it has a number of like the sub catchments from S1, S2 until S5 or 6. And the sewer system, you can see here, there's either green or blue one. The blue one shows the culverts. For example, is under like a bridge, for example, is like a closed conduit. And in the green, like the elements, link elements, they represent swell. So this is like one example of a swell, for example. And also another type, which is shown by black one for this catchment, they can transfer the surface runoff of this catchment is a gutter. We only have one gutter, and this is a one representation of the gutter. It's like the side of the road, for example. We have a curve and we have a gutter, but we don't have any kind of like the swell. But the swell normally like the vegetative and the grass area, and has got the dimensions like this one. And from the geometry, you should be able to just define different geometry. For example, in our example here, for the swell, we represent the trapezoidal cross section like this one, and you need to define some parameters here. For example, like the depth of that, and Z1 and Z2 is like the slope of the left and right hand side. B is the bottom width at the bottom, and H is either the height. In the case of the circular, the D applies. The D is a diameter. So if you don't have like a diameter, you can remove or ignore this one. And just pay attention to this. And N is the Manning value. The Manning is for the roughness of your channel or whatever, like the conduit or elements link that you have. And just pay attention to this point. That, for example, for the case of the gutter, because one slope or one side is the vertical, we are not able to define 100% vertical 90-degree angles. For that purpose, we just define a Z as this kind of like the length or elements, a side of the slope as a very, very small value, like for example, and the model understand this one, and which just represents, and the vertical like the side is 1, and the Z is a proportional like the value. if you just define the Z1 or the horizontal, like the side of this triangle, like a very, very small value, you can represent a lot more or less similar to the vertical one with a good level of accuracy. And the horizontal, the other one, Z2, you can define it very like a mild one. For example, 25 is very mild, so it shows that the gutter has got a very small and mild steep slope. So this one is very steep and this one is very mild. And the B for the gutter is 0 and H is 1. For example, 1 foot in this example. And for junctions as well, so for junctions, we can define the inlet node and outlet node. So this is for the example has already been done. For example, what is the upstream or inlet and outlet and the length of that. And it's either has got the H or D. If it's like the culvert, it has got a like the D. Or if it's like the swell or gutter, it has got a like the depth of that. For this specific case, the culvert, we are supposed to just calculate the diameter, and it is likely to be determined. So it's like not shown in here in this case. So let's look at more details of what we're just going to design. This is like some theoretical calculation for the Manning formula. As you know, for the Manning formula, we're just going to use this one. And for any kind of like the steps that we're just going to use, I just leave this kind of like the sections. If you want to just modify or to estimate the relevant, the Manning value, you can just find this from any lookup table. For example, in this case, we have a lookup table. This is like one example, but if you look at any relevant reference, hydraulic reference, you can see relative Manning value, for example, for canals, swell, rivers, depending on like the specifications or pipe system, you can just use the N of the Manning value and has got a specific unit, but it's like for either English or like a metric unit, the values are the same. The only, as you know better, that the only for the English units, this coefficient has got a like a different, like has got a one coefficient at the top. Okay, so let's just look at more specifically to the design practice that we're just going to go for task 2 before going and showing you this example in the SWMM software. So based on your design skills, we need to just manually improve the design of the system under a post-development. So this is the post-development, you know, for example, all like the buildings is going to be built here and they have a like the sewer system here. And for the conditions in example 2, we want to just use this assumption and procedure that's based on this. So first of all, design objective is to minimize the peak flow of the free outflow points at the most downstream points here, like the junction 01 or the most downstream point. We have a specific peak amount or the flow discharge in this point. We want to minimize that one. Okay, so the purpose is that we want to minimize that one as much as we can for a specific flood, which is, or storm, which is 100-year return period of a storm with a duration of the 2 hours. And so the design parameters that you can manipulate in your design includes, first of all, you are supposed, or you can, you are able to just change the Manning coefficients. You know, the Manning coefficient of all of the Manning values here for all the conduits, okay? Or by using this range, for example, because we assume that for swell, they are vegetative based on the lookup table that we had in here. We just have like a swell for a specific like the range. We are able to choose whatever we want. So you can manipulate and choose any like the Manning value between this range, like a 0.05 to 0.15 for a swell. And for concrete cross section, it means for culverts, you can choose any value between 0.12 and 0.012 and 0.017. So this is for swell and culverts, and for and the same for gutter as well, because gutter we assume that is like a concrete. For dimensions, how we can just use, as well as like changing the coefficient, you can change the dimensions of the open channel conduits, as long as you can just keep the same surface width. Why? Because in practice, you are not allowed to just change this top surface or the surface width. Actually, it has to be the same, because based on the urban town planning, you are limited to some specific space in here. So you need to just keep the same top surface, whatever has already been defined, okay, or designed. So you are able to just change the slope of the side and the bottom width. You can play with that. It's completely up to you. And this is something, your flexibility to just change that one. So we have a one Excel file for you to just, based on the parameters that we define, E, H, and Z, you should be able to use that Excel file. I'll show you in a moment. So let's just go to the detail of that before going to the example. So you need to just systematically do these the steps. First of all, use some new values for the roughness conditions, roughness of the conduits based on the range that we define here for the swell and for the column, and then run the stream software and use the summary button and report and make sure that there is no flooding. If there was no flooding, you need to do based on the trial and error, try to just change the dimensions. Okay, before we go to just explain this one, let me just show you how the procedure is going. So first of all, the task 2 is just written here in this kind of a Word document. Please have a look at this file as well. So let's just open the file here. So this is the stream software. And once again, once you open the file, you should be able to open this example 2 post SI units. We converted the file to the SI units. The original file from the stream website is in English units, but we just convert everything to the SI units. So you just double click on that and open the file like this. You can see everything here. As you may know, you can practice with all the icons here. This is for example, to define the rain gauge. We have a one rain gauge already defined here. Subcatchments, you can just see it here. We have a number of subcatchments here. And conduits in here, you can define by this shortcut. If you want to add any new one, this has already have a number of conduits, and the node, the thing that we just have in here. And all these elements, as I said, is shown on the left-hand side as well. So, for example, for hydrology, you can see the rain gauge. We have only one rain gauge here or one rain gauge here. For hydraulic elements, we can see the node elements, the junction, all the junctions here, and you can see the junction listed here. We have 11 junctions. If you click on any of them, it can be shown in the map. For example, this one, this is a junction 6, junction 4, and also for the conduit as well. If you go to the link conduits, you can see all the conduits here. We have 11 conduits here. If you click on them, it can be shown in here, conduit 11 and conduit 6 and other conduits. And also the same for subcatchments as well. We have 7 subcatchments already. This is subcatchment 1, subcatchment 2. And the other hint before we're just going to start and run this model for this example is option. If you right click on the panel, option, this is something useful. There is one icon here, is annotation. And you can display the ID of the rain gauge, subcatchment node, and link. So I can normally turn on or click all of these options because they are useful. We have 4 main elements here. So once you just press OK, you can see all the elements here, and that's really useful and good. So if you click on any items either here or the items here, okay, double click on any items, for example, junction, you should be able to see the properties of the junction. Very simple. In here, for example, all the properties of the junction, for example, X and Y, and elevation, invert elevation. This is something very important, and other the specification. And also the same for the conduit. For example, you can see the conduit and the inlet node. Inlet node means the upstream, outlet is the downstream, and the tag is the tag is something that we write it. And there's a short description at the bottom. Is very, very useful. And also the shape. The shape is really important. You can see here, it says click to edit the conduit cross-section in geometry. So once you're just going to click on the 3 dots here, you can easily change the geometry of the conduits if you like. This is something that we want to just do in this example. So you can see, for example, for this conduits, in the example, it's shown that this was the trapezoidal, this is a swell, and here the bottom width, the maximum height, and the number of the barrels is like the number like open. There's a 1, and the left slope or Z1 and right slope is Z2. If you remember, this conduit number 3 was the culvert. The culvert, for example, there's a like a bridge, and there's a like a, for example, circular cross section here. So the cross section is like a circular, and we only have the maximum height. Okay, so this is another like the thing you just bear in mind. And okay, so we're just going to close all of this. So we're just going to make sure that the rain gauge is set for the 100 years time period. If you're just going to go to the rain gauge, we can see all informations here. If you double click on that, you can define the rain gauge in 2 different ways. One way is to just use the time series, and the other one is you can use a data file. For example, you want to just use some specific historic rain. You have some historic rain, you can just put it here. Or you can use some specific time series. Okay, so it just read from like some specific file, or you can just use a specific time series here. For example, I already defined 3 time series. The model has already defined this in the time series section. Where is exactly? For example, if I'm close here, the time series already defined time series section on the left-hand pane. If you click on that, you will see the time series already defined here. By the way, the other thing, if you want to just add any new elements, there's like the green and the red, like the icons here, red like to delete, and the green to just add, the green plus to just add any elements. For example, and you can add and define and put a name like the 2 years, 10 years, 100 years, or any other like the time series that you want. And if you double click on that, this is a name. We put it here, and this is like with the 5 minutes time step, we define all the values here. And all the values here are in millimeters. Why? Because the units that we define here. This is another point is important. If you refer to the user manual of the stream, you will see the flow units. The units of the whole system is defined based on the flow units. If you want to use for example, SI units, you need to just use, you can choose a few of them. As you can see, there's a lot of separation. CMD, cubic meters per second, and liters per second, and million liters per day are the 3 SI units. And these 3 are for English units. So just stick to like the metric unit if these units, if you want to use the metric units, for example. So, but we normally use the LPS or liter per second. So, okay, for this example, I'll show you where exactly. Liter per second, the flow units, whatever shown here is based on the liter per second. So here we define everything here. So just bear in mind for the liter per second unit, and for 100-year return period, everything is in millimeters. Just bear in mind. Millimeters is like for rain gauge. So in here for the time series, you don't have any value here. So all the value here is shown, or you need to just bear in mind, insert all the values only based on the millimeters, okay, not meters. So this is like the millimeters. This is based on the definition of the software tool. So we just allocate and set here for 100-year return period. Okay, that's all set. And we already have defined the model, so we run the model. There is an icon, thunder sign icon here. You can just click on that, and the model just is run very quickly, like a fraction of a second. And you can accept that one, and you want to see what is the performance. First of all, you need to just look at the report section, a summary, report summary, report menu summary. You need to see everything here. And if there's any flooding happens here, if you use this drop-down button, you should be able to see any flooding here. At the moment, I can't see any flooding, so everything perfect. So no flooding at all happens here. If there is any flooding, the flooding icons will appear in this here, and you need to just resolve that one. So I close this one. So there's no flooding, absolutely perfect. I need to see what is the outcome for 100-year return period with a 2-hour duration. So I click on the 01 outfall point. So you can see here, so I need to just plot this one. You click on this one once, you don't need, and if you double click, you can see the specifications, okay? To see the results, you just choose or one point here, for example, the outlet or the flow discharging outlet, and at the top, there is like a one short key here. This is a time series plot, and this is a time series table. So plot, this is something that we want to see here. So we can look at here, and you can edit what type of parameters for a specific node of interest. For example, 01, we want to see. You can click on edit. Okay, so for example, for this case, the variations of the depth. If you want to see the variations of the for example, we want to see the hydrograph, you need to just choose this one and, for example, show the either flooding or in this case the total inflow. There is another icon relevant to the flow is lateral inflow. Just bear in mind, lateral inflow is another type of the inflow that comes from other the link to this node directly. But if you want to see what is the inflow, the total inflow, choose that one. Okay. So we choose this one and accept this one. So it's for O1, for node O1, which is the outlets. Okay. And the total inflow. If you want to just compare other nodes, you can easily add that one. Click on that and add it to here, and you can just define to compare with the outlet. So for this kind of the purpose, we want to just do this one. And as you can see here, the total peak, this is a hydrograph of the variations of the flow of the outlet. You can see here the maximum or the peak is something above the 5,000. So this is something that we can have, and for the comparison, I'm just going to show you. If you're just going to put the 10 years, run the model, and you don't need to just close that one. If you don't close the previous graph, once you're just going to open it up, you can see the 1800, a little bit above 1800. But don't close this one. You don't close this one. Just click on the a point here and choose 100. So we can see here, for example, we run that one and just only see this one. You see the results here. So this is the 5,000. So okay, so let's get back to this kind of introduction. You are familiar how to run this one, and if you want to change anything like the conduit or let's say the Manning value, if you click on any kind of the things, you can see the roughness. The roughness here, we set this one as the Manning roughness coefficient. So you can easily change the Manning coefficient based on the lookup table that you have, and you learn this one. And if you want to change the dimensions, as we discussed, for example, for trapezoidal, you can just go in here. You can either change the depth. Normally, we can just leave the depth as it is, but you can just change the other things here. As I said, you can just keep the top width, and but you should be able to just change or manipulate the bottom width and also the left and right slope. Okay, so I'll show you how to just do this one in a minute. So let's just look at the one that we have here. Okay, so let's just show you in Excel file if you want to just manipulate the dimension, how it works. For example, in this kind of Excel file that you have that one, you have the Z. The Z is the slope on the left-hand side. By default, it is 5 for all the slopes currently defined in the example. And H is defined 0.9144, and the B is a 1.524. And the T, this is something calculated based on the bottom width, and the slope is the B plus 2HZ. And the T is calculated automatically by this formula. I just put it here. For any new the value for the Z, if you just calculate the new Z automatically, I just put a formula here, very simple to calculate the B as well. So if you change the slope, easily, if you can have another a slope, for example, wider one or the wider slope, obviously the B will change. If you assume that the top width is fixed, by changing that one, milder one B decrease, for example. I choose for example, 1, the B becomes the 8 point something, one is the steeper one. But if I'm just gonna choose a little bit milder than 5, let's say I'm just gonna choose 6. You can see it's impossible because the B becomes negative. So I cannot go with that one. I can choose 5.5. It is possible. It looks like a triangle. It's but you can just get to that value. But obviously, if you want to just increase the capacity, you are supposed to just have a steeper slope, for example, 2 or 3, for example. You can see the bottom width B becomes the wider or the bottom width. So, and this is something that you can just get to that value. Okay, let's go back to this kind of example. For example, I'd like to just choose something to see what's going on. First of all, I need to just see what is the maximum one. First of all, I need to just write down what is, for example, I get a table result of this outlet. It was above 5,000, but I need to just write it down. For example, I'm just going to go to the table one, and table one, you can choose the total width. I uncheck the depth. Okay, so total inflow here, and here you can see the total width is it has to be somewhere above 5,000. You know, you can see here. I can write it down like the 51.02 point. I mean, that's enough liters per second. I can write it down. I'm just trying to just manipulate a little bit and see if I can just decrease this one, if it's possible or not. For example, I choose another conduit. This conduit. This is a swell. Okay, so based on this technique that I have in Excel file, I just okay, let's just have like a larger capacity. I just choose like a 2, and the width changes. Okay, so I'm just gonna go to for example, I change the slope and this one and the new V. So I'm just gonna go in here and slope for the bottom width. So I'm just gonna put that one rather than this one. I'm just gonna put that 7, and the slope I just define it here as 2. Not maximum height. A slope is 2, left and right, and the bottom width, you know, is increased to this value. So, for example, this is a one change I did. I'm just gonna see what is the impact on that. So first of all, I run this one. I need to check if there is any kind of like the flooding happens here. No flooding. Everything is perfectly well, and I just close that one. Let's just see if I can open this one by object for the outlet. Not this one. I like to just choose this one. Add that value here. Oh no, so this has to be select this one first, and then table by object. So the total inflow. I'll have a quick look at this. Okay, so I can see this one. Can you see this one? So it's increased from, it was 5,100, but it unfortunately is increased to 5,346. So it's increased. So this kind of like a change is a like a negative. It just increased a like a flow discharge. Another like the points, I'm just going to show you another like the capability of the software is a create like a profile plot. So if you just choose this one as well, you can just choose the starting node, for example, from this point, starting to the most downstream points. And by the way, to see the like the flow direction, you can choose the right click options, and if there's a flow arrows, you can just choose whatever. And here you can see the flow arrows from the upstream to downstream. So you can see the like the flow direction, outflow. I'm just going to choose it here. Find the path. All the conduits can, or the links can be found here. And there is a like the map here, and you can, there's an animation for that. You can just run this one and see the what happens, and the, like for example, all the like the situation, the conduits and nodes, and we're exactly just going to increase. And if there's any flooding happens, you should be able to see the profile as well. So as far as I can see, no flood happens here. This one has got a like a maximum, but the flood is not happening here. To just for the purpose of this example, I'm just going to open the example once again because I just manipulated this here. I like to just change the roughness, for example, to see if the flood happens here. For example, I just choose the roughness here is only like the 0.05. I'm just going to choose here 0.15, for example. So because of this, I can slow it down. Okay, so probably that might be good, but I need to just make sure. First of all, I need to just make sure it's a 100-year return period, and go to the report summary and just look at here. Oh, I just make the like the swell rougher, but unfortunately there's a node flooding happens. So where is that? Yeah, J5. Where is the J5? I need to just flow arrow all the like the nodes on. So J5, where is it located? I just oh, I can see here. I just manipulated the, I think this pipe, and the flooding happens exactly here, and it has all the specification of the flood. For example, you know, for example, here we just make this kind of like a pipe rougher, but this is like a situation. Let's just see in further details through the profile. This is the start, and this is the end. So you can see here. So this is the procedure, and going to the map, and you can see here J5. J5 should just this pipe. We made it rougher, and we need to see how we can just first of all, we need to observe the flood happens here in this case, and how we can just then later modify that one. You can see here. Can you see? This flood happens here, and we have some reports here. So let's get back to this presentation. If you have like the see any kind of like the flood happens, okay, if there is a node flooding that we can see here in this case, we need to do some specific procedure. First of all, start from upstream of the conduit where the flood happens and change the dimension of the conduit. Okay, we change the dimension of the conduit and try to just make it and make it, although we make it rougher, but we need to just make it increase the capacity and run the model and check the flooding if happens or not. So for this case, for this pipe that I just made it like a rougher, I'm just gonna go here and I'm just gonna go with that, like the changes that I just introduced here. For example, I'm just gonna make it like the Z, the slope is 2 and the width is this one. So let's just copy the width here. So I'm just gonna go and go to the change. Z, I'm just gonna make it 2, and the bottom width, I'm just gonna change it to this value. Okay, so let's see if it can just remove the flooding or not. Just go to the again to the summary. No flood. Okay, that's really good. But let's see what is the outcome. So click on that. I think I didn't know. I just unfortunately I didn't open it actually. So I just click on that, and again, like it's not shouldn't be depth, total inflow. Accept this one, and see what's going on. Oh yeah, can you see this is a drop? Drop is definitely below 5,000. And if you go to this one here by objects, you can see total inflow, and we can see the evidence here. After half an hour, I think it's 30 something. I think the maximum is here. 4,931. You can see compared to that one, just a little bit we can reduce. So this is a lot of practice for us, how we can reduce this one. So we make the system rougher, but in other sites we just make it, and once you're just gonna make it rougher, you can reduce it for example, contribution to just get to the peak time. No, this is the peak. We can just slow it down, and contribution of the water comes to the peak. We can reduce that one, and that has an impact. But because once you just make it rougher, it can have the overflow and flooding here. We increase the capacity of the swell here. So just very simple technique. So this is some practice for you. So please spend time on that and try to just increase or increase the capacity, and also by using that kind of a dimension and change the pipe roughness coefficient of the manning. Try to just reduce the peak of the outfall. It is very important for us because we are supposed to reduce this outfall to get to the pre-development. This is based on the many the council and developers and many kind of consultancy and authorities, actually water companies or environment agency or the council. They expect the developers to just reduce the peak flood to the situation before development. So this is the practice for you. Please just please work on that by trial and error and see how you can just decrease the situations in this example. So this is the task 2. So let's see if everything is covered for task 2. And just before we finish that task 2, just look at some of the key facts here. The hydraulic cross-section, or the best hydraulic cross-section to maximum discharge or the maximum capacity, there are for each cross-section, we have some specific the shape, for example. For the rectangular, for example, the maximum capacity happens once the width is twice the height. And for trapezoidal, the maximum ideal that the maximum capacity happens when we just have the angle of the 60. So this is the example or task 2. Please just work on this, and we can discuss in the class about that as well. Thank you.
Thank you very much, Kurosh. Now it's up for the student to have fun with the model. Thank you very much.
Yeah, sorry for that. I thought that it's going to